very concrete by stating the theorem in the first minutes of the talk. So, okay, so let me do part one. And then, so we consider the L function associated to the direct character with conductor 3 and the imaginary. And then we consider its value at 2. So concrete speaking, this is just a sum of like you have 1 over things which are congruent to 1 mod 3 and then minus 1 with things congruent, sorry, I can't count. Things congruent to like 2 mod 3. And then so this concrete number that we can prove that it is actually irrational. And what we proved a little bit more is actually these 3 numbers, 1, zeta 2, and these L2 chi negative 3 are Q linearly independent. Okay, so since I'm talking about in a module form, automorphic form workshop, I'm going to say it's like how is that related to, like which part goes in related to module form. So classically speaking, when we want to prove something, some number is irrational, one way to do so is like you somehow have a sequence of rational number approaching it, and if it approaches to it too fast, then the Liouville bound, and then you conclude that actually it shouldn't be rational. I'll make this more precise later. And then, okay, so the thing is like, for instance, I can give you one example. So we're going to talk about this example in more details later. So this Apres work of zeta 3, now we know zeta 3 is irrational. And then what he did is that he constructed a sequence of rational numbers which goes to zeta 3 very fast and concludes that zeta 3 is irrational. Okay, and then after Apres work, there's been like lots of development on constructing a sequence of rational numbers going to all kinds of interesting special value of L functions. I'll give some example later. And this has been in literature, especially the one that we are using, goes back to the work of Zagay. And that's the part where module form is used. And then what we do is like, there has been many rational approximations to interesting periods in literature, but most of them are not as good as the one that goes to the like target fast enough as Apres. Hence, like for people who constructed these like rational approximations, they cannot conclude that the limit is irrational. But today we're going to talk about the new part in our work is to how to make use of those like rational approximations in literature. So that part doesn't have module 4. Okay. Although we do work on like module curves. We'll talk about that later. And then to intentionally confuse you, it's like I'll give you a second theorem, which is also about irrationality. And then from the statement, you'll see 2 different theorems. And then the goal of today's talk is I'm going to explain to you why for our method these 2 things are very similar. Okay, so the second part of the theorem is the following. Now we consider log values. Okay, so here we have m not equals to n, and these are integers. Okay, the conclusion is like this number is also irrational if. So here's the part. In general, there's conjectures about like log values of rational numbers to be like how transcendental they are, and essentially speaking, if they do not have the obvious log rule, then they should be as transcendental as they should be. But unfortunately, we cannot prove it for all the cases. What we can prove is that with the extra condition that the ratio of mn is very close to 1, we actually give the explicit number, then this number is irrational. We actually prove that this one and each factors are Q linearly independent. Okay, so at this moment, these 2 theorems seems to be so independent from each other. But the key point that I'm going to say is that I think it was mentioned in the morning talks, is like one thing is like Modular forms actually satisfy differential equations, and we're going to make use of the differential equation of the modular forms, and then these two things would have singularities similar to each other in our setting, and hence we can actually run the proof similarly. So I hope today the goal that I'm going to achieve is like by the end of talk you'll see is like why these two theorems are like similar in our setting. Okay, so before I move on, let me just make a couple of remarks on the results. Is like, for first thing is like, there's definitely when you study L values, the first thing that you would come to your mind as like special value of L function will be the class number formula, which tells you everything about like this question with respect to say quadratic characters, and then you know all these numbers are transcendental by Lindemann-Weierstrass theorem. And then you can also do is depends on whether your like Dirichlet character is even or odd, it can tell you half of the like integers, namely for Riemann zeta function, you know like zeta 2, zeta 4, they are all powers of pi, and then hence they are all transcendental numbers. And then this is an example where the classical work of Euler and Dirichlet doesn't apply. Okay, and then of course it's like you can use like geometric interpretation, motivic conjectures, say for instance the Grothendieck period conjecture to make predictions, but very little is known like other than predictions. And the second half is like, as I also mentioned for logs, you have this like Chenius conjecture, which tells you like what you expect. It's like essentially speaking, if you don't have any obvious like log rule relations, then you don't expect any relations. And then previously what was known is like the famous theorem of Baker talk about the linear forms of log. And then this is the first result that we know about when you talk about like product of logs. Okay. And then, so let me start from, as I already mentioned, April's work. Let me actually tell you a little bit more details about April's work, and then explain like the part one of the theorem. Okay, so I'll make it a little bit more abstract at the beginning, but I'm going to make it more concrete. So let me just first state the fact that I said at the beginning, is that if we have a number, so this number is the interesting period we want to study, and it's given by the limit of rational numbers, and q not equals to 0 in integers. And then, so what we know is like, if the approximation is very close. The very close is like it's smaller than 1 over q to the n to 1 plus epsilon for every n. Then the conclusion is like alpha is irrational. That's something that you can prove by contradiction very easily. So this is like what we say by, we have a sequence of rational number which approximate the interesting number in a way which is fast enough. And then what April did is like he actually constructed a sequence. Let me just formulate the sequence in a way which using the generating series, and these are closely related to module forms. So although like in April's classical work he didn't do it, it was reinterpreted by breakers on like how do you view these like from module form point of view. Okay, let me first say what happens is like he actually constructs two power series. One is z coefficients, the other is q coefficients, but not too bad in the sense is like we have this denote LCM of these numbers to the third power manipulates all the coefficients, the denominator of all the coefficients. Okay, and then so zeta 3 need to show up somewhere is as power series in Rx that we have that both power series converge, has the convergence radius equals to this number, and then this following mixture has a larger convergence radius are these numbers? These numbers are just the elliptic points of a certain modular curve. Okay, and then what happens here is the following, is why are these information helpful for us? This one actually implies, so if I write a and spell out the coefficients, this one, okay, we first observe this is strictly larger than 1. And hence, this tells us that we do have the limit of Bn over Nan equals to zeta 3. Okay, so now it's like, let's look at the fact is zeta 3 is the alpha. And if you kill the denominator, so let me actually write one more step. I can write this one as clean up the denominator of Bn. And then so this gives us the Pn and the Qn. So all we need to estimate is like how large is the Qn here, and then how close is this ratio to zeta 3. Okay, I'll leave it as an exercise called that the like calculus tells you is like if you know the convergence radius, you can estimate the size of the coefficients. And also it's like using prime number theorem, we can estimate the size of the LCM. And hence it's like we'll say, I'll leave this as an exercise, it's like star holds. Okay, I'll write it in a very stupid way, if and only if that the log of this convergence radius is greater than 3. Okay, so let me use color chart. Is the 3 is this 3 here, and then this number is the convergence radius here. So like I hope you believe me that using like the knowledge from calculus, you'll be able to like study the asymptotic size of these ones, and then you compare it to star, and then you end up to have this numeric condition, which is true. And hence it's like once Apri has constructed these sequences, he concludes that zeta 3 is irrational. Okay. Now, let me go to L2 chi. So, I said it's actually already in the work of Zaghi, where he actually constructs for you like the analog of A and a B for L2 chi. And I'm going to just say reformulate what he wrote in his paper in a way in terms of like module form. And thank you for introducing actually integral in this talk. Okay. Everything will be very concrete for us. So I'm going to write everything for like L2 chi negative 3, but I hope it's like you will see it's like it works more generally. At least you can replace chi negative 3 with other like Dirichlet characters, and then there's a little bit extra work you need to do if you want to like remove 2 with larger like positive integers. Okay, so we consider this module form you'll see in a minute why this module form. So this is a weight 3 modular form. On gamma naught 6. And then we're going to take its Echelon integral. So here I'm just borrow the like definition from Yan's talk that you just copy the coefficients but add n squared to it. Okay. Essentially, let me just rewrite it as q dq twice x on b equals to this module form that we start from. Okay. So it's like this is weight 3, and we this operator was applied twice. So this one should be something of weight -1. It is very clear in the periodic setting, as in Yang's talk. And then we'll see is like, although there's some like things going on with like when you actually apply the like elements inside this group to it, you will have some extra terms, but it doesn't make things worse. It actually is controllable. Okay, so in this sense, let me actually write it down. So what we have is like if we apply -1 with gamma inside the gamma naught 6, what if we have is this will give us b, but plus some polynomial in tau. Tau is the thing in the upper plane of degree at most 1. This is not hard to believe. It's because that you just apply this operator twice, and then you get this module form, and then 3 change with 3 here, and then the difference between 3 and -1 is like every time that you apply this one, you adjust it by 2. And hence it's like you would get this relation. This is okay, so and I denote this one with b as a reason is that you should think about this b to be closely related, not exactly that b, but closely related to that b here. And then, so here's with -1 module form, and then you just pick, so pick A to be a weight 1 module form. And for instance, let me just follow against work. We actually have A that he picked to be the one corresponding to theta series. Here, -3 means that you have the lattice associated to the quadratic field adjoint to -3, and then you take the maximum order and construct the theta series with respect to that like quadratic order. Okay, and then so this is a module form, and the claim is the following: so the claim, which actually was how Sergey did it, is like there is, so this is weight 1. There exists a L, which is an order 2 differential operator on x naught 6, such that L x A, so let me say this is coordinate, this is isomorphic to P1, so it has coordinate x, and then we write A as, so a priori here is like it is the coefficient power series with respect to like the Q expansion, and but we actually write it as a power series in x. Okay, so the linear, the differential operator actually kills it. The reason is because it's like for every module form of weight k, you always has a order k plus 1 differential operator which kills the module form when you view them like with respect to the coordinate on the module curve. That's not hard to prove, because one way you can do is like you start from this one, and then you can multiply it by tau, multiply powers of tau, and then you argue that up to just the like tau to the weight, and then you argue they actually satisfy a linear relation, because you can actually study what happens to the gamma elements x on it. Okay, so there exists an order 2 differential operator kills it, and also we know that L x on A times B is equals to some polynomial in x. And the reason is the following, is let's look at what happened. You look at this equation here. So I'm going to just multiply everything by A. And then, as I said, it's like by the proof of where this linear differential operator coming from, it's like the solutions are actually A and tau A. So when you apply the L, so I will use second kernel. So if you apply L, this part actually goes away. So you actually only for, that's why it goes back to it actually looks like something of weight -1. Is when you apply the differential operator, this extra piece goes away. And then we actually have something which is A is weight 1, B is weight -1. Hence, you actually end up to have a modular function. That's why no matter what differential operator you apply, it will be a polynomial in X. Okay. So upshot. So here I give you the explanation on why these things are true, but the upshot is there's one way to, and then let me think I'm going to this one. In this case, this is actually equals to 1. Okay, so the upshot is you start from a modular form of, say, weight k here, and then you have something which corresponding to the echelon integral, and it will be, in this case, it's minus k minus 2. And then, so you start from k here, and then you do a k plus 2, and then when you do the echelon integral, you have something which is minus k, and the minus k and the k paired together, you would end up to have 2 power series, each of them killed by certain differential operators, and more precisely is whichever associated to the holomorphic module form will apply on the product of the holomorphic one and the corresponding echelon integral to get something which is very controllable, a polynomial. And in this case, you can concretely compute it, and it equals to 1. Okay, so far it's just echelon integral and the differential operators. And then the second part is where the period comes from. Okay, the period coming from the following observation is we actually have let me state what we actually have. So we actually have is AB minus L2 chi -3 over 2 HA, sorry, A. This is actually convergent at 1 over 9. Here is we have y06 is isomorphic to P1 minus 0, 1, 1 over 9, and then infinity. And here we choose the coordinate so that it's preserve the integral structure coming from the Q expansion. Okay. Sorry. Yes. Good. So let me say what happens here is first is we have this differential operator, and this differential operator actually is defined on the correct one I should write is y06, because the argument is just working on the upper plane. And hence the differential operator would have singularity as 0, 1, 1 over 9, and infinity. These are the cusps. Okay. And then when you have these things, since they are already regular at 0, and then you ask, what is the convergence radius of solutions of these are linear ODEs. What are the solutions of convergence radius of linear ODEs over C? It goes to the first singularity. Okay, and which is 1 over 9 here. And then you can actually run the same argument, and this tells you is here is also corresponding to the suitable module forms. And then this is also convergence radius be the first singularity here. And then what happens in a priori is the periods show up. Some periods corresponding to the motive here show up such that it actually has a larger convergence radius, which means that this particular linear combination actually is convergent at here. There are 2 ways to understand it. One way to do so is that you can study the monodromy group of this differential operator, and you see it's like what is condition to kill the local module at 1/9, and that'll give you the number. And but since here we are already talking about the module curve and the module forms, let me just tell you what this number is. Is actually, so let me just rewrite it as what we have is b minus the limit as q goes to 1, because q goes to 1. So this is x equals to 9 corresponding to q equals to 1, tau equals to 0. Okay, so bq, when you apply weight -1 with respect to the arithmetic operator, it is actually equals to b minus. Okay, so what did it say? So we know this behaves like a weight -1 module form. And then, so, but up to certain extra information. And then the functional equation will tell you that it actually should be a constant here. And then what exactly is the constant is not hard to compute. The correct constant you're going to do the adjustment is put this number here. And then this is actually just that there's no extra term. If you just look at this one, it is invariant under the W6 section. Okay, and then the W6, the arithmetic evolution swap. So we swap these two cusps, and hence is that because we are already regular at 0, so this one will be regular at 1/9, and that explains why this one is converted. Yes.
Ask, I mean, maybe it's a naive question, but what would happen if you tried the argument in the naive way on the gamma 0 of 3 without introducing level structure at 2? If you just take M3 gamma 0 of 3.
The problem is that
because your period would then just be the constant term. So you'd have only two cusps. So you'd have
it's just I need to find the module form.
The B, you mean?
The both the B and A.
Yeah.
Yes, so the thing is, as far as you have a module form on whatever level, then you'll be fine. The only reason that we have a 6 here is that this is where we can find our A and B. Yeah. Okay, so let me just summarize. It's like this particular shape of B is to make sure that when you take the limit as q goes to 1, this number shows up. And then, because this is the correct thing to make your construction convergent at 1/9, the first cusp. And then the whole theory of actual integral and module forms tells you like these are actually solutions of different linear differential operators. Okay. So now let's just, then it's like back to Arthur's work, which I didn't tell you, Berkeley's interpretation is like you can actually construct these A and B using like module forms as well. Okay, and then all these conditions will be very concrete since we have, let me just summarize. So what we have, the properties is in Rx, those both A and the AB converge. The convergence radius is equals to 1/9, and this particular linear combination is AB minus our period as the coefficient has convergence radius equals to 1, because it goes through this cusp, this singularity, and hence the convergence radius will go to the next one. And then if you just look at, because it's just the property of actual integral that you did actual integral twice, and hence it's like we know the coefficients. So the nth coefficient of AB is killed, has denominator divides the LCM of 1 to n squared. The LCM coming from is like, this is n squared if you do the Q expansion, but then when we expand everything in terms of the half-term modulo, and then you mix up the first n coefficients in similar way, so the best you can say is like it divides the LCM of all these. Okay. Yes. And this is what the modular form interpretation tells you, that how you can realize all these special value of L functions in a way which is very similar to April's work. Okay, now it's let's look at the numerics. It's unfortunately, so let me draw a sad face. Okay, sad face for maybe previous people, but happy face for us. There's something that we can do. So sad face is if I'm going to just copy the numerics, so I have log 1 versus 2, and unfortunately this is not true. Yes, so I mean, I left the exercise to you, but I said the upshot is you put the larger convergence radius here, take its log, and then you put whatever way that you control the denominator on the other hand. It's if it goes naively to conclude something is irrational, then you would want this to be true, but this is not true. So we need to do something else. Okay.
So where are the 2 and 3s from?
So 2 and 3 coming from the, how bad is the denominator of your second power series?
So it's square or cube?
Yes, yes. And that's related to the weight of the module form that you use. Okay, and then so what we did is just what can you do if this is not true? And then let me put a happy face, which is a little bit mysterious right now, is that log 16 is greater than 2. And then I think the next part is I'm going to tell you why you can multiply 1 by 16 in this case. Okay, any questions so far? So if you get lost about the module forms, then it's a new start. It's all we need to remember are these properties along with the claim that it intensify a differential operator. Okay. Now it's what happens here is we study a power series, and then we have a convergence radius, but we want the convergence, somehow the convergence radius to be larger. And let me just state it this way. Actually, I'll just put this up and use a new letter. So now I'm going to just reformulate for you this easy fact, but in terms of power series. That's related to the title of the talk, why I call it the arithmetic of power series, is I'm going to reformulate the fact in terms of power series, which we already see the numerics here, but let me just emphasize it once more. This is a fact. Still, it's coming from it's just the abstract version of this simple calculation that I left as an exercise. So if we consider a power series, Q coefficients, and then we assume that we have some control of the denominator in the way that, so if this is not an integer, just take the smallest integer, the largest integer below it. And since we're all talking about asymptotic, it doesn't really matter. So if we have some control of the denominator, and then the conclusion is if we take the product of all places, V of Q, and then for each place, we consider this is the convergence radius of this F. Now you view it inside the V-adic power series. And then we take the log. If this one is greater than b sigma, then f is a polynomial. Okay, this is exactly a reformulation of like using convergence radius related to like the size of the coefficients and the prime number theorem. And then stated in this way is like most of the applications that we have, like the functions are g functions, and these conditions are always satisfied by certain sigma b and n. Okay, so this is a classical easy exercise. Now it's like it looks a little bit familiar, saying that we have a power series. We know something about its convergence radius, the conclusion that it is a polynomial. So now here's the multiple generalization you can do. You can just replace this one by the radius of meromorphy. Namely, is instead of being convergent, you only want the radius of the largest disk such that over which f is a meromorphic function. And that's actually the work of Berkeley, and there's also in the work when he proved like the rationality of zeta functions. And then so basically it's like you can replace this one by like the radius of meromorphy. And then there's the other work is like if we are in the case sigma equals to 0, and then there's okay, I'll actually jump ahead of myself. Let me skip this part. Then it's like, why do I actually need to work with disks? I mean, so the whole kind of like when you take, say, complex analysis for the first time is like all the simply connected domains behaves the same as the disk. So that's why it's like there's the work of Claudia and I'll make sure that I spell the name correctly. And Bertrandis, that you can actually replace this by so-called the size of simply connected domain to convergent domain. Okay, so simply connected is the word for the Archimedean case, and then for the like periodic places, you take certain affinoid, and then you can still measure the size, and then you would get the same conclusion. Things are rational. This is already good because it's like let's just look at this example here. Is what type of things that we can pick? If we just pick the disk of radius 1, it is bad because log 1 is smaller than 2. But now we can already do is like, let me just draw the picture. So this is our C. And then we have 0 goes to infinity, and then we have a 1 here. Okay, so we can actually take this domain. Because it's a solution of differential equation, and hence it will be convergent on anything as far as you rule out the singularity. Okay, and the size of this one is equals to 4. We already made some progress. It's like 4 is greater than 1, but unfortunately log 4 is still smaller than 2. So there's extra things that one need to do here. Okay, and then this actually goes to the work of Ivan J, where he said it's like we can actually just use substitution. And let me just state what he actually did. So the setting is the following. It's like you think about like what are simply connected domains. Simply connected domains are the ones which is isomorphic to a disk. So you reformulate it as that you have an injective map from a disk to your whatever coordinate it is, and when you pull back, it's actually convergent. And then, but there's nothing wrong with like just drop the injectivity condition. So let me actually state the setup. This goes back to the work of NJ in 1989. Okay, so now it's like first, instead of consider excuse me, one power series, we can just consider a bunch of power series with similar properties. And here I'm writing everything with Q coefficients. Of course, you can replace it with any number field that you like. We have some control. We still copy the same control of denominators. But to make life easy, instead of doing like m integers, I'll just make them to be integers, which is sufficient for our application. Okay, and then we consider a map phi, or this consider is more like choose a map phi, which is from the closed unit disk to C, where C is our just the coordinate x, such that 0 maps to 0. And the derivative at 0 is not 0. Okay, so what's the property? We want some convergent property. So we choose phi such that when we pull back our functions fi by phi, this is actually meromorphic on the disk for every I. Okay. And then, so if we have, now it's because we only work with the Archimedean thing. So if log, the replacement of the like convergence radius will be just the size of the derivative at 0. If this one is greater than b sigma, then our first stated, then we have explicit upper bound on the dimension of the qx span of all these functions. How is this one related to the above? The above says that if I just choose phi to be injective, and then if this is true, then the dimension of the span of all these things equals to 1, because everything is a rational function. This is how this one is related to the above case. And then if you replace it by something which is not necessarily injective, you can, so actually let me just, you can try an example. So for instance, you can try the power series to be given by this one. This is a z coefficients power series. And you can try this one because it's like the only thing that is 1/4 and then infinity. So that's why it's like you can take the like uniformization map. Hence you can pick your like radius to be as large as you can. And then that's why you wouldn't expect that upper bound to always be 1. It will be an upper bound which depends on phi and the b sigma. Okay, so what happens to our setting? In our setting is like these fi's like we already have is, okay, so in our setting is to apply NJ's work is the following. We prove by contradiction, assume for contradiction that this L value is rational, then we can have like say, let me say, we can pick fi equals to, I want to leave it as I here, and I'm going to tell you some other f's. equals to the AB minus L3 times A. This is with Q coefficient. And then such that B equals to 1, sigma equals to 2. And what is our phi? So we can take phi to be very closely related to the lambda function, which is from the disk to C minus 1, coming from Q goes to lambda Q. This is the agenda. And we know that the derivative at 0 is 16. Okay, so what happened? It's like when we assume full contradiction, then we have a function Q coefficient with large convergence properties. And that allows us to choose a good map phi. And so what is the actual phi? The actual phi would be, because we have this small issue at 1/9, you just look at your disk, rule out all but one pre-images of 1/9. By a topological argument, you'll see that the pullback of F will still be convergent under this phi. And then you won't lose much for the coefficient. That's why we're in this happy setting that log 16 greater than 2. So what we know goes back to Ivan-J's work is that, so since let me repeat it, log 16 greater than 2, we actually have an explicitly upper bound for the function. Okay, so now, the previous case, if we go back to Alpery's case, is like we have something is a polynomial or a rational function, but by construction that we know for sure it is not a rational function, then we get the contradiction. Now let's see what we have here. So our work, which is actually based on our earlier work on the unbounded denominator conjecture, which is on ICAF in 2021 and published this year. And there's also the work of Bost and Francois Shah, which I think they posted on ICAF in 22, and I think it's also going to be published soon, is our work which tells us that the explicit upper bound in terms of phi, b, and the sigma is strictly less than 9. Okay, so you do not get as good as I give you examples. You wouldn't get dimension 1 once you work with things which are no longer injective, but you get an explicit bound. And the explicit bound with the particular choice of b, sigma, and the phi, and we can actually get an upper bound to be at most 9. Okay, then let's see how many functions do we have. So we can have f1 equals to 1. This is a function which is nice, satisfying the assumptions here, the denominator assumption and the convergence assumption. And then we can have f2 equals to log 1 minus x, because it satisfies the differential equation with singularity at 1 and infinity, so that's also good. And then we also have f3 equals to log 1 over x square, because square doesn't change the singularity, it just makes the denominator slightly worse, but it's not worse than so the denominator is the LCM of 1 over n squared. And hence you can actually have f4 to be just the Li2. This is sum x to the n over n squared. This is also okay. And then we can also have, so now it's like f5 is equals to our AB number to A. And then we can have a f6 because it actually satisfies a differential equation of order 2. Oh, I already erased it. So you can take the derivative of f5. Okay. And I lost track of my numbering. Then there's, let me say this is f6. And there's another honest function f5, which is coming from, you can read our paper. I will not give some explicit power series. It's an honest explicit power series, which is coming from some hypergeometric sequence. Okay, so we're almost there. We so far have 7 functions. And then it's actually not too bad. It's like we can have, so we can shrink phi also to avoid negative 1 over 8, sorry. The negative 1 over 8 coming from that we want to do the symmetry. f8 equals to f6 x minus 1. And f9 equals to the derivative of f8. Okay. Now the upshot is that if we assume for contradiction this is a Q coefficient power series, then we actually end up constructing 9 functions of this template, namely this restriction of denominators and this restriction of Archimedean convergence property, which contradicts with the explicit upper bound that we provide. And then also the contradiction. And just imply that f6 should not be Q coefficient power series, i.e. is L2 chi negative 3 is irrational. Okay, so let me just summarize what did we do? It's classically we have a sequence of rational approximations, and then if we only work with convergence radius and do not think anything about the differential equation is satisfied, then we just die there. And there's nothing you can do. But then it's if we actually take into account and satisfy a differential equation, and then based on Evagri's work where he come up with the idea, it was inspired by the work of Chudovsky brothers, that you can actually work with something more general than just the convergence radius. Then you have a higher chance because it's always that some convergence property should be better than the denominator measurements. And then the larger convergence property that you can explore, you have a higher chance to beat the denominator property. And then if we allow ourselves to do so and make use of the differential equation, we actually find a function phi which make us into the region that this case is satisfied. But unlike the classical case, you always draw a contradiction immediately because everything you construct from modular forms or other kind of geometric method, you would never expect it to be a polynomial or rational function. So that was easy to conclude there. But in our case, the best you can hope for is just an upper bound. But luckily in this case, it's we find enough functions to contradict with the upper bound if we assume for contradiction. So honestly speaking, these 4 functions should not exist with respect to that template because this is it should be an irrational number, and hence we conclude that. Okay, so I was lying a little bit here, is that the actually explicit bound we get is equals to 9 in this case, but then what we do is assume you actually have these functions, then you can take one step of integration, and then we show that when you take one step of integration, the extra functions that you get would actually beat the upper bound that we have there, and then it solves the problem. Okay, so let me just say one thing goes back to the log problem. It's as you can see here, let me just summarize, it's all the numerics is so there's some theory behind it, but all the numerics is about what are the singularities of your differential equations, and in a way that we only care about it very numerically speaking. So for us, like 1 over 9 and 1 over 9.01 is just exactly the same thing. Okay, and then the other thing is about the number of functions. Okay, so let me just go back to the log question. So the log question, log theorem, is the assumption m over n very close to 1. So enable us to let us construct a function h which depends on m and n such that it satisfies a linear, second order linear ODE with singularities in and also, so basically it's like, actually it's like this condition. So basically it's like, if you have a log value, the classical work on irrationality constructs for you a differential equation which depends on your m, like where the singularity is. And then you take the adma product of these two like generating series, and then result like adma product will tell you like what singularities you have for differential equations of the adma product, and the condition would guarantee that you actually would have singularities near 0, 1, and infinity. And then it's also convergent on the singularities around 0. So it's very similar to the above case. It's like it has singularity 0, 1, infinity, and one singularity 1 over 9, which is very close to 0. And hence, it's like you would imagine as far as your kappa is small enough, you can literally use the same phi as above and do the computation. So like the same phi, because of the denominator, is because it's like one log gives you one copy of LCM of 1 to n, product of 2 log will give you 2 copies. And so literally you can use the phi and then get the dimension strictly less than 9 bound. And then you would literally, since it's also a second order ODE, so these functions will still be there. So it's literally the same proof. And then once you actually set up everything in terms of the numerics of the differential equations and denominator type, this hard work computation that you do here, it took this some time to actually find the optimal phi and find the nice bound. And then, okay, you get a second theorem once you kind of like constructed the, like reinterpret the like classical rational approximations in terms of the like linear differential equations that we want. Okay, so let me just stop here. Thank you.